Okay, so we want to make kind of a digression and talk about a topic that really goes back to evaluating limits, but we now have kind of the necessary machinery with derivatives to really get into it, and it's a really useful technique. It's one of those things that you're going to learn now, and you're going to think, man, I wish I could go back in time and know this earlier when I was taking limits. So let's just think back to a typical limit example. So let's say we're taking the limit is x approaches 1 of x squared minus 1 over x minus 1. So recall that if we just tried to apply the limit laws and take the limit of the numerator and the limit of the denominator, we got something that was a big problem. We got an indeterminate form. And so what did that mean? Well, what it meant is that the limit, well, it didn't mean that it didn't exist necessarily. It just means it wasn't able to be determined in the function's current form. So somehow we needed to use the fact that we don't care about the function at x equals 1 and maybe try to rewrite the function assuming that x is not equal to 1. And that's exactly what you do, right? So you just take the numerator and factor it as x minus 1 times x plus 1, this difference of squares here. And so this is the same thing as just taking the limit as x approaches 1 of x plus 1, because we can cancel the factors of x minus 1, since x is not equal to 1. And we get 2. Now, we want to really just focus in on indeterminate forms here. And if you recall, we actually have seen examples of other indeterminate forms. So I believe we looked at something like this. And we have a similar situation. So if we just try to take the limit of each one of these functions individually and then subtract them, we get something like, okay, this is going to infinity, and then we're subtracting something else that's going to infinity. That's also an indeterminate form. That doesn't make sense. So indeterminate forms are something, more or less, that just don't make sense. Okay, we don't have a way to, or a well-defined way to assign a value to 0 over 0. It sort of depends on how the functions are how is the numerator approaching 0, how is the denominator approaching 0. So it really has to do more with the rates of change at which the functions are going to 0. And that's going to be the key idea with L'Hopital's rule. But first I want to give you a table of values of indeterminate forms, just so you can see, maybe this isn't all of them, but at least a big number of very common indeterminate forms that can come up. All right, so here's our table. In the left-hand side, we have different indeterminate forms, so 0 over 0, and then in the right-hand side, we have examples. So the limit as x approaches 0 of sine x over x, recall, that gave us the indeterminate form 0 over 0. And we have a bunch here. Okay, so x squared plus 1 over x squared minus x. If we just try to let x go to infinity, then the numerator is going to infinity and the denominator is going to infinity. So that's a kind of indeterminate form. We can't just assign this a value based on the fact that we're getting something that looks like infinity over infinity. Same thing here, infinity minus infinity. I don't know what that means. I can't just say it's 0 because sometimes it's not 0 in limits, and we've seen that. 0 raised to the 0, that's an interesting one. So what is 0 to the 0? I know that 0 to a number other than 0 is going to be 0, and a number that's not 0 raised to the 0 is going to be 1, but what is something going to 0 raised to something going to 0? It really depends on the rates of change of those functions, how they're approaching 0. Just like here when you have infinity, it's going to depend on the rates of change and how quickly those functions are going to infinity. 0 times infinity, same problem. How fast is the function going to 0? How fast is the function going to infinity? 1 to the infinity. This is an interesting one. I think this is probably the one that people have the most trouble with, right? Because you want to say, okay, 1 to any power is just 1, because I'm just multiplying 1 times 1 times 1. But it's not that we're saying 1, the fixed number 1 to the infinity isn't 1. We're saying that something going to 1 raised to something going to infinity in a limit may not be 1. It depends on the rate of change of both of those functions. So the idea is to handle indeterminate forms, and really this is the cool thing about what we're going to learn here, is that we're going to learn one method to attack all of these limits. And the idea to handle indeterminate forms is to look at the rates of change. Of the functions. And now, what do I mean by the functions here? I mean the functions that are creating the indeterminate form. So, for instance, 0 over 0. To look at the rate of change of sign, because that's going to 0, and look at the rate of change of x, is that's going to 0. And that's what we're going to study. So it's not surprising that derivatives are going to play a big role. Okay, so let's introduce this amazing technique that's going to allow us to evaluate limits in a variety of indeterminate forms. Alrighty, so what we're going to discuss is called L'Hopital's rule. Okay, and this is a little tricky, especially if you are a native English speaker. So this was a individual. It's named after him. So that's why, you would think, oh, why isn't it called the limit rule? Well, it's just named after an individual. So L'Hopital's rule, it's a little funky to think of. What I like to do is just to tell people, from here on out, we're just going to say this is LR. So if you prefer, you can just say by LR, but it's L'Hopital's rule. So what does L'Hopital's rule, or LR, say? Well, if we're taking a limit of a function that's the quotient of two functions, so f of x over g of x, and what do we get? We get 0 over 0, or plus or minus infinity over plus or minus infinity. So all I'm saying is that we try to evaluate a limit, and we get one of those first two types of indeterminate forms, 0 over 0, or infinity over infinity. And then, of course, it could be negative infinity over infinity, or negative infinity over negative infinity, whatever. doesn't matter, they're all indeterminate forms. If we get an indeterminate form like this, and, well, we need f and g, we need to be able to really study their rate of change. So we need f prime and g prime to exist. So f and g are differentiable. So we're dividing by g of x, so I'm going to require that g prime of x not equal 0, not everywhere, but just near x equals a. Okay, so I'm being a little vague by near. I mean, what I really mean is that there is a sufficiently small open interval around x equals a for which g prime of x is not 0. Okay, then what? Then this is what we can do. This is the magic. Then the limit as x approaches a of f of x over g of x is equal to the limit of the quotient of their rates of change, or their derivatives. So f prime of x over g prime of x. Okay, and this is really just kind of encompassing the idea that, okay, if f is going to 0 faster than g is going to 0, this limit should be tending to 0, essentially. So we're just formally saying that by looking at the rates of change as the derivative, and then we're taking the limit of the quotient. That's the same thing as the limit of the quotient of the rates of change, or the derivative. Okay, so under relatively mild assumptions, it is very important that you check and make sure you have an indeterminate form. L'Hopital's rule does not apply if you do not have an indeterminate form. That's very important. And I'll show you an example of what can go wrong if you try to use L'Hopital's rule on a limit that doesn't lead to an indeterminate form. But for now, let's actually just see how easy L'Hopital's rule makes finding limits. Okay, so let's start by looking at some very familiar limits. We know that the limit as x approaches 0 of sine x over x is equal to 1. But I want you to think back of how we justified that limit. So we actually drew the unit circle, we kind of drew some strategic auxiliary triangles, we used the sandwich theorem in kind of a creative way. It's a very tricky proof to show that the limit as x approaches 0 of sine x over x is 1. Okay, but just think about this. Let's use L'Hopital's rule. So the way I like to use L'Hopital's rule is, first of all, you must verify that you have an indeterminate form. This is essential. So I need to actually write down explicitly that I have an indeterminate form. Like I said, if you don't have an indeterminate form and you try to apply L'Hopital's rule, you're going to get incorrect answers. You have to start with an indeterminate form. Then this is what I like to do. I like to say that this limit is now equal to by LR. Okay, so I'm just putting LR over the equal signs, just signifying that, okay, this is equal by L'Hopital's rule. The limit as x approaches 0 of, okay, I just take the derivative of the numerator, which is cosine x, and I take the derivative of the denominator, which is 1. But what is this limit? Well, this is continuous at 0. I can just plug in 0. Cosine of 0 is 1. I just get 1. So how easy is that? I get the indeterminate form. I actually just plug in L'Hopital's rule, apply it, take the derivative of the numerator and the denominator, take the limit, and I get 1. Now, before you get too excited about this, there's actually sort of a problem with evaluating this limit this way. So because what you probably want to say is, well, why do we do this crazy geometric proof for the limit of sine x over x if we could have just used L'Hopital's rule? But think about the fact that we just used to apply L'Hopital's rule. What did we have to do? We had to take the derivative of sine x. And so if you remember how we took the derivative of sine x, we actually had to know the limit as h approaches 0 of sine h over h. So there's definitely a bit of circular reasoning here. But again, I'm just illustrating that in the future, now if you have a limit like this, you can just apply L'Hopital's rule. All right, here we have another limit. We want to evaluate it. Now, don't just jump in and apply L'Hopital's rule, because we need to verify first, it's right here, that we have an indeterminate form. But that's actually pretty clear here. If I let the numerator go to infinity, I'm going to get infinity. And if I let the denominator go to infinity, I'm also going to get positive infinity, which this is one of our recognized indeterminate forms. Okay, so then I just say that this is equal to, by L'Hopital's rule, the limit as x goes to infinity of, okay, so I just take the derivative of the numerator, that's 2x, and then I take the derivative of the denominator, which is also 2x. Okay, so then I try to plug in infinity. Again, I get infinity over infinity. Again, I need to justify that this is an indeterminate form. And because I still have an indeterminate form, I can actually apply L'Hopital's rule again. So this limit by L'Hopital's rule is equal to the limit as x approaches infinity. Now this time the derivative of the numerator is 2. Derivative of the denominator is also 2. But 2 over 2 is 1. Limit of a constant is just that constant, so we get 1. So this example shows that you can actually apply L'Hopital's rule time and time and time again until you get to something that you can evaluate. But it is still essential that every single time, even if you have to apply L'Hopital's rule 10 times, before each time you verify that you have an indeterminate form. Where you get into trouble is you look at the limit you're trying to take and you say, oh, it looks like I can just apply L'Hopital's rule 6 times and I'll have something simple. But the problem is you may actually, within those 6 times of taking the derivative, have something that's not an indeterminate form. And that's actually when you want to stop. You want to stop once you don't have an indeterminate form, because once you don't have an indeterminate form, you're able to determine the limit in that. All right, here we go. Here's where things get really interesting, because let's just try to evaluate this limit. What do we get? Well, maybe you need to think a little bit about the unit circle. So as x approaches pi over 2 from the left, okay, so what does that mean? That means sort of like coming from 0 up to pi over 2, like this way. So as we approach pi over 2 from the left, we're actually coming up counterclockwise towards pi over 2 on the unit circle. So what's happening to secant? Well, secant is 1 over cosine. So the x-coordinate on the unit circle is going to 0, but staying positive is the essential thing. So it is going to infinity. And then tan x, for the same reason, so sine is approaching 1 as x approaches pi over 2, but in the denominator, we're dividing by cosine x, which is going to 0 and staying positive, so we're going to be subtracting something else that's going to infinity. So this is an indeterminate form. So we can apply L'Hopital's rule. But wait a second, how do we apply L'Hopital's rule here? Remember, L'Hopital's rule applied to a ratio of two functions. If we had sine over cosine, or sine x over x, x squared over x squared, whatever. But this is secant x minus tan x. So what do? So remember that the first two cases of indeterminate forms fell into the realm of L'Hopital's rule. What about the last four? Infinity minus infinity, 0 to the 0, 0 times infinity, 1 to the infinity. It seems like L'Hopital's rule doesn't apply to those cases. But here's the trick. You can always turn an indeterminate form of those last cases into an indeterminate form of the form 0 over 0 or infinity over infinity. Let's see how we do that in this case. And this is typically the hardest part of using L'Hopital's rule, is when you have to do a little bit of work to get it into an indeterminate form of the right form. So this is the same thing as taking the limit as x approaches pi over 2 from the left. Let's just actually write down what secant x is and tan x is. So secant x is 1 over cosine, and then tan x is sine x over cosine. So hopefully you see now that we can actually just combine these into a ratio. So the limit of 1 minus sine x over cosine x. And now we see this is 0 over 0. Of course, it's still an indeterminate form. We haven't really done anything to change the fact that it's an indeterminate form. We've just turned it into another type of indeterminate form that we can apply L'Hopital's rule. Okay, so now we can say this is equal to, by L'Hopital's rule, the limit as x approaches pi over 2 from the left, derivative of the numerator, so 0 minus cosine x, so minus cosine x over, okay, and then the derivative of cosine is negative sine x. Okay, but now we no longer have an indeterminate form because the denominator is not approaching 0 as x approaches pi over 2 from the left. It's approaching 1. So the numerator is approaching 0, and the denominator is approaching, well, really negative 1, but that doesn't matter because the whole thing is going to be equal to 0. So it's always funny to kind of joke around with these indeterminate forms, because here, in this particular case, infinity minus infinity equals 0. But it's very important to note that that will not always be the case. It really depends on how fast secant x is going to infinity and how fast tan x is going to infinity. All right, so here's another really cool function. X raised to the x. Now this function really only makes sense for x strictly greater than 0 for some maybe technical reasons, but okay, that's fine. It's kind of an interesting function. And of course, if we just try to let x go to 0, we're going to get something that's going to 0 raised to something that's going to 0, and this does not make sense to me. This is an indeterminate form. So again, we run into the same problem. We would like to apply L'Hopital's rule, but the indeterminate form that we have now is not consistent with the indeterminate form that we need to apply L'Hopital's rule. And this is trickier, right? Because before it was just a simple rewriting of secant and tangent. But x raised to the x, how can I rewrite that? I mean, that's kind of a very concrete thing. It's just x to the x. That is what it is. How do I rewrite it as a fraction? Well, this is where we're going to introduce an essential technique, okay? And it's very much reminiscent of logarithmic differentiation, okay? So actually for the next 3 examples, we're going to use the idea of kind of using logarithms. All right, so what we want to do, first of all, I'm just going to assume that this limit exists. You can actually prove that it exists, but let's just assume it does. So let capital L equal the limit as x approaches 0 of x to the x. And consider, so we're not going to find L, we're actually going to find the natural log of L. Okay, so the natural log of L is just the natural log of the limit as x approaches 0 of x to the x. Okay, I mean, it seems a little strange, but if L is this, natural log of L is natural log of the limit. And here comes maybe the slightly technical part, and the part that, in my experience, people don't fully appreciate, the subtlety here in what we're going to do. But we're actually going to use the fact that the natural log is continuous. Okay? And so what am I going to do? How am I going to use that fact? Well, taking the limit of something inside a continuous function is the same thing as taking the limit of the function evaluated at what you were taking the limit of. So this is because natural log is continuous. So you can just think about it for continuous functions. If you have a limit inside the argument of a function, so you're composing a function with a limit, then you can actually just move the limit outside in the case that the function is continuous. That is basically what continuity is saying. You can move the limit inside the function or outside the function. But now look, I can now apply properties of logarithms. So this is the same thing as the limit as x goes to 0 of x times natural log of x. Well, So at first glance, we have not done anything very helpful, because if I just take x to 0, this is 0 times log of 0 is approaching negative infinity. And of course, I'm being a little lazy, all of these should be x approaches 0 from the right. And actually here we see why that's the case, because we're using this logarithm, and as x approaches 0 from the right, it wouldn't make sense to talk about the limit as x approaches 0 from the left, because the domain of log x is only the positive numbers. So now we have the indeterminate form 0 over 0 times negative infinity. But what we can do here is pretty quickly change it to an indeterminate form of infinity over infinity, or really negative infinity over infinity, by rewriting x as 1 over x. Okay, so it's kind of silly, but x is the same thing as 1 over x. So these are really exactly the same thing. And this is, again from the right, negative infinity over infinity, which is an indeterminate form. Okay, so now we have the indeterminate form in the right form to apply L'Hopital's rule. So this is now equal to, by L'Hopital's rule, derivative of log x. Well, first we have the limit as x approaches 0 from the right. We have the derivative of log x, which is 1 over x. And then over derivative of 1 over x is minus 1 over x squared. This is a quotient of fractions. So keep, change, flip, multiply by the reciprocal, favorite algebraic method for simplifying division of fractions. This is the limit as x approaches 0 from the right of negative x squared over x. And I mean, we could apply L'Hopital's rule again, but really we can just cancel a factor of x, and this is just the limit as x approaches 0 from the right of negative x, which is 0. Okay, so are we done? No, of course we're not done. We did not find this limit. We found the natural log of this limit. So if the natural log of the limit is 0, how do we get back the original limit? Well, we just want to use the inverse of the natural log. So if natural log of L is 0, that means L is e to the 0, which is 1. So the limit that we're looking for is equal to 1. Alrighty, so here we have another limit as x approaches 0 from the right, but this time we have x natural log of 1 over x. So if we just naively try to evaluate the limit, we get 0 for x, and then as x approaches 0 from the right, log of 1 over x, so 1 over x is going to infinity as x approaches 0 from the right, 1 over small positive number. So log of a number going to infinity is also going to infinity. So this is an indeterminate form. But of course, it's not in an indeterminate form that allows us to use L'Hopital's rule. So we just got to be creative. And this is almost exactly the same thing that we did towards the end of the last example. Instead of seeing x as just x going to 0, see it as 1 over x that's going to infinity. So write this as log 1 over x over 1 over x. Okay, because again, x is just 1 over x. And now we can use L'Hopital's rule, because this is, well, let's verify. This really is infinity over infinity, which, again, indeterminate form. So what does L'Hopital's rule tell us? Well, that this is the limit as x goes to 0 from the right. Derivative of the numerator, well, that's going to be 1 over, so the derivative of log of something is 1 over that something times the derivative of what you were taking the log of. And I'm just going to write it as 1 over x prime, and you'll see why I'm doing that in a second. And then the derivative of the denominator is 1 over x prime. I'm not even going to take the derivative. And why am I not going to do that? Well, because these cancel. So I have the same factor of the derivative of 1 over x on the top and bottom. So this is just the limit as x approaches 0 from the right of 1 over x, but we've already said that that's just x. So the limit is approaching 0. Okay, so one more example. We had one more type of indeterminate form, and that's what's going to happen here. So as x goes to infinity, 1 over x is going to 0, so cosine of 1 over x is going to 1, and of course x is going to infinity. So we're getting an indeterminate form of the form 1 to the infinity. And same old story. We would like to apply L'Hopital's rule, but in its current form, we can't apply L'Hopital's rule. So we need to do more work to get it into another indeterminate form that we can apply L'Hopital's rule. I know it's just absolutely a mess. So here we go. We're going to do the same trick as before, letting L equal the limit. And if you're wondering, okay, well, how do I know when I need to do this trick with taking the natural log? It's very similar to the rationale behind when you use logarithmic differentiation. When you have a function raised to another function, there's really nothing you can do with kind of an exponentiation of functions. You need to change it to a product of functions. And the best way to do that is to take the natural log. So in this case, natural log of L is, I'm actually going to skip a step. So recall again that I'm just using the fact that the natural log is a continuous function to say that this is x times natural log of cosine 1 over x. Okay, so you can always just do this. When you have a limit, you take the natural log, you can just go ahead and take the natural log of what you're taking the limit of, because, natural log is continuous. So this is really a key fact. Natural log is continuous. And in the future, you may not even say that explicitly. It's just an established fact, and you use it, and it's very, very helpful to use. but it is a key fact for this course. Okay, so now we have an indeterminate form that looks like 0 times, well, this is going to 0, and so log of 0 is going to negative infinity. And it's probably worth noting that as x goes to infinity, this is approaching 0 from the right, so cosine is approaching 0, is approaching, no, hold on, I'm sorry. X is approaching infinity, right? 1 over x is approaching 0, so cosine of 0 is 1, log of 1 is 0. So this whole thing is approaching 0. So we're getting infinity times 0, but we know how to deal with this. When you have an x in a 0 times infinity, you just want to rewrite it as, well, whatever the other function is, so log cosine 1 over x, and then rewrite x as 1 over x. And now we get the indeterminate form, 0 over 0. So this is an indeterminate form. So let's apply L'Hopital's rule. So this is equal by LR. Again, that just signifies, so, you know, if you're taking a class, probably, you know, you want to get the right answer, but there's also a step in justifying your work. And so when you show your work, it is important, since this is the last example, I'll just say this now, it really is important to say why what you're doing is true. Okay, and if you have this powerful tool like L'Hopital's rule, you want to say, okay, yeah, I'm bringing in the big guns, L'Hopital's rule, everything's going to be okay. So we want to take the derivative here, so this is going to be, let's see, 1 over cosine times the derivative of a cosine, which is sine. So I think all in all that gives a tangent 1 over x. And then we got to use the chain rule, so multiply by the derivative of 1 over x. Well, we'll just leave that as 1 over x prime all over 1 over x prime, okay? And again, so how did I get tangent here? Well, the derivative of log of something is 1 over something, so 1 over cosine. Then I got to multiply by the derivative of cosine, which is sine, so I have a factor of sine over cosine, which is tangent. But then I have to use the chain rule again, because it's not just cosine x, it's cosine of 1 over x. And these cancel, so the natural log of the limit that I'm looking for is the same thing as the limit as x approaches infinity of tangent 1 over x. But as x goes to infinity, 1 over x goes to 0, tangent of 0 is 0. So natural log of the limit is 0, therefore, as we've seen before, the limit is going to be equal to e to the 0, which is 1. So in this case, you know, we get to play the kind of funny game. 1 to the infinity actually is 1 in this case, but it will not always be the case.